Well, welcome back for Hess's Law. Hess's Law is important because it allows us to determine the energy requirements or the energy released for chemical reactions without actually having to perform them, because they might be too dangerous, we might not have enough material there, but we can make conclusions about energy transfer based on much smaller reaction steps. So remember, energy change is a state function. The amount of energy that changes, if you go from a lower energy to a higher energy, is independent. The path is independent of the changes you went through. So we got maybe one step here, a step here, a step here, another step there. Regardless of what the steps might be, that energy change, delta H, is just going to be right there. So we can subtract this one, add this one, subtract, add and subtract again with each step to get the total energy change for reaction. So what I'm saying is that chemical reactions can be broken down into steps. Each step can be either exothermic or endothermic. Endothermic, exothermic, endothermic, exothermic. But if you add them all up, you get the net energy change in a reaction. Put a period there. Now, we can look at the parts of a reaction, and that allows us to determine the energy required or given up in any reaction that we can write an equation for. So if we look at the half reactions, we can write the net energy change for big reaction. But there are two things you've got to remember. If a reaction is reversed, the sign on the delta H gets reversed. So it's going to be negative going one way, positive going the other. So for instance, nitrogen plus oxygen yields 2 nitrogen monoxides. Now delta H for that reaction is 180 kilojoules. However, let's say the reaction goes the other way, and we have 2 nitrogen monoxides, and they break up into nitrogen and oxygen. Well, we still have the same 180 kilojoules. It's got to be transferred, but it just goes in the opposite direction now. So it's now a negative sign. So if we flip the reaction, we just have to change the sign on the delta H. The other piece is that delta H is proportional to the moles of reactants and products. So we have 1 nitrogen, 1 oxygen makes 2 nitrogen monoxides. That requires 180 kilojoules. However, if we want to put 2 nitrogens and 2 oxygens together to make 4 nitrogen monoxides, that requires twice as much, or 360 kilojoules. Because we multiplied these guys by 2, we've got to multiply this guy by 2. So, how do we actually use that in solving a problem? Well, a typical problem will give you the half reactions, like this. Sulfur plus 3/2 of a mole of oxygen give you sulfur trioxide. And that gives up 395.2 kilojoules of energy. And you get another half reaction, 2 sulfur dioxides plus oxygen give you 2 sulfur trioxides. And that gives up 198 kilojoules of energy. So then you'll be asked to calculate the delta H for a particular reaction. Sulfur plus O2 yields sulfur dioxide. Now, I have to use the information I was given in order to solve this problem. What we're trying to do is find a way to add these two guys together and their energies to give us this chemical reaction. So, the first thing I do is I look at it and I say, of these chemical reactions, where do I have stuff on the side it needs to be on? And what jumps out at me is these sulfurs here. So that tells me that I'm going to keep sulfur, this equation, in the correct order. And I rewrite that, and it's delta H. So, then I look at this and I see, well, I don't have sulfur trioxide. I got sulfur dioxide up there. Actually, I don't have any sulfur trioxide up here at all. So I've got to find a way to make it cancel out. So what I do is I look at this and I see I've got sulfur trioxide here, a sulfur trioxide here. I got to keep this one going forward, so it tells me I need to turn that one around. So that's what I do. I write it backward. 2 sulfur trioxides yields 2 SO2s plus O2. Okay, now that's working for me. Now because I turned that over, I've got to change the sign on this. So it's no longer negative 198, it's positive 198 kilojoules. So as I'm looking around at this, I say, okay, how can I make this cancel? Well, I've got 2 sulfur trioxides here, and I've got 1 sulfur trioxide there. I don't have any SO2s here. Oh, I've got an O2 here, and then I've got 3 O2s here, so those don't quite balance. The point is, I got to get rid of the sulfur trioxides. So what I'm going to do is, I'm going to multiply the whole thing by 2. So we'll put a 2 out here, and then we have to put a 2 here. So what happens now is I get rid of this 2, I got a 2 here, I cancel that 2 out, and there's a 2 here, because 2 times S is going to be 2S, 2 times 3 halves is going to equal 3 O2s, and 2 times 1 SO2. 1 SO3 is going to be 2 SO3s. Now, if I cancel out the things that are the same on both sides, what happens is my 3 O2s here become, cancel that guy out, become 2. Oh, wait a second. I don't think I had this quite right.